Hmm. Weird. I can't find this the camera here. Hmm. All right. Here's the attendance form. Got some uh grab a pack of them on your way out. You'll get it right now. I guess we should do more nonlinear unless there's, well, I have two nonlinear examples I want to do, and then we'll see how we feel about how much time is left. So let's look at the maybe just one example actually. Happens to me all the time. So the Co-17C, today is the 26th. Just looking ahead, so Monday you have an exam, Friday we'll review, and after Monday, you have what, 5 classes left? Because next week is week 9. You'll have Wednesday, Friday, Monday, Wednesday, Friday. And then your final, whatever day that is. And the last 5 classes, we totally changed directions. We're start talking about probability and yeah, like probability stuff, which it just feels like very unrelated to anything else we've done. But it's kind of like, well, we need something to fill the content for the last 2 weeks, and that's what the math department picked. So that's what we'll do after this next test. Let's look at this system. So we're going to find all equilibria of the system. We have dx1 dt equal to 9x1 times 6 minus x1 minus 4x2, and dx2 dt equal to 3x2 times 5 minus 6x1 minus x2. And determine the stability of each equilibria. I really should say the local stability of each equilibrium. No, all right, cool. So for this one, to me, I will remind you that these kind of questions where we're finding all the equilibria, right, where they're nonlinear, we're finding all the equilibria, really to me feel more like finding the critical point of a function of two variables where we've already taken both partial derivatives. So it's like we're setting each partial derivative equal to 0 and finding the simultaneous solutions. There's one obvious one here. 0, 0 to me is pretty obvious. If x1 is 0 and x2 is 0, we have a solution. So one of our equilibria is going to be x1 hat, x2 hat equal to 0, 0. But there's going to be at least a few more. At least there's going to be 3 more, actually. So here's how we're going to find all of them. We're going to set each factor in combination equal to 0. So meaning, like, to find this one, I set 9x1 and 3x2 both equal to 0. Question. Yeah, because if it's a system of homogeneous linear equations, meaning so this is in contrast to a homogeneous linear system, which looks very generally like this. dx1 dt equal to ax1 plus bx2 and dx2 dt equal to cx1 plus dx2. If that's your system, what you really have here when you're trying to find the equilibria is, well, you're setting each equation equal to 0, and then you're finding the solutions. Now, even if these lines, well, I should say, clearly 0, 0 is a solution. If x1 is 0 and x2 is 0, both of these equations are going to be 0. And I will also point out that both these equations represent the equations of lines, right? If I actually isolate our y thing, which is x2, I could write this as x2 equal to negative a over b times x1. Or y equals negative a over b times x. That's a line that goes to the origin. You know what? So is this. X2 equal to negative c over d times x1. Or y equals negative c over d times x1. And as long as those slopes aren't the same, the origin is the only point of intersection of these two lines. So the origin is the only point of equilibrium. And we almost never deal with the case where these are the same, so we're not going to worry about it. So for a homogeneous linear system like this, which we could certainly write as dx1 dt, dx2 dt as a vector equal to the matrix A, little a, little b, little c, little d, times x1, x2, right? If you can write your system like this, then 0, 0 is the only equilibrium. I'll add in a small caveat here, assuming the determinant of your matrix is non-zero. If that determinant is 0, then other weird stuff happens, but we're not going to worry about it. So that's the general answer to your question, is that yes, for linear systems that are homogeneous, the equilibrium is the only, 0, 0 is the only equilibrium. If it's non-homogeneous, which we saw a couple classes ago, you only get one equilibrium, but it's not the 0, 0 point. It's some other like 2, 3 or 5, 7 or something that's not the origin, but still there's only one. So any linear system of differential equations where you have something times x plus something times y, maybe plus a constant, and something times x plus something times y, maybe plus a constant, you only ever get one equilibrium where those lines cross. On the other hand, these differential equations are nonlinear. Right? If you wanted to, you could think of this as like 9x times 6 minus x minus 4y, and 3x times 5 minus 6x minus y, right? That's a totally different situation where if you graph that, kind of weird. I think here for a second. Yeah, and again, if I'm thinking of these as partial derivatives, kind of, they really are, but that's kind of how I manage them. That's a good question, and I would probably need, I feel like I need to look at the definition of homogeneous again. I think homogeneous means that 0, 0 is the only solution. So these would be not homogeneous. But I'm not 100% confident that I really should look at the definition and check that. So I don't know. The more important part is they're nonlinear. And I'll double check the homogeneity part of it. Yeah, that's a good question. So maybe homogeneous has to be linear to start off with. There might be something there. So anyway, we'll not worry about that for right now, but I will look at that later. So to find the other solutions, or I should say to find this first solution, what I really did was I set the factors 9x1 equal to 0 and 3x2 equal to 0. That's how I found that first equilibrium. To find the other ones, I'm going to just pair one of these factors with one of those factors. So I could say I'm going to set 9x1 equal to 0, and instead of setting that equal to 0, I'm going to set that equal to 0. 5 minus 6x1 minus x2 equal to 0. But setting this equal to 0 yields x1 equal to 0. And then if x1 is 0, I have 5 minus x2 equal to 0, or x2 equal to 5. So another equilibrium is going to be x1 hat, x2 hat equal to 0, 5. We'll get another one by setting this factor equal to 0, 6 minus x1 minus 4x2 equal to 0, and that factor equal to 0, 3x2 equal to 0. We're going to get x2 equal to 0, meaning we're going to get x1 equal to 6. So another equilibrium is x1 hat, x2 hat equal to 6, 0. And finally, the hardest combination is setting the two pieces both aren't just easily 0 equal to 0. So the last part here, I'm going to set 6 minus x1 minus 4x2 equal to 0, and 5 minus 6x1 minus x2 equal to 0. And then we're going to isolate one of the variables and plug it into the other one to find our solution. So I'm going to isolate x2 here. So I'm going to say that 5 minus 6x1 is equal to x2. I think it looks worse today than it usually does. Not better? Maybe. And then plug that in over here. So we get 6 minus x1 minus 4 times 5 minus 6 times x1 equal to 0. Now we can solve here and get 6 minus x1 minus 20 plus 24x1 equal to 0. So 23x1 equals 6 minus 20 is negative 14, so positive 14. That's terrible. X is 14 over 23. Here's what I really don't want to do, actually. I don't really want to plug in 14 over 23 there to solve for x2. It just seems kind of gross. Usually these problems don't have such terrible numbers, usually. So instead of fine, I'll do it anyway. It's kind of, yeah, this. I really don't want to, but I guess I will. 5 minus 6 times 14 over 23. Multiplying 5 by 23 over 23, we get 115 over 23. Minus 6 times 14 is 60 plus 24, which is 84 over 23. And 115 minus 84 is 16 plus 15, which is 31 over 23. So our final equilibrium is 14 23rds, 31 23rds. So unhappy about that. This is a web work problem I took from a different class last year. So there's our 4 equilibria. And now we're not going to do the linearization, because linearization is kind of a pain. It's actually not a pain, it's just kind of unnecessary. We're going to classify the stability, the local stability of each equilibria by finding the Jacobian and then plugging in each critical point of the Jacobian and then looking at the trace and the determinant to see if it's stable or not. Okay, so let's go ahead and do it. Oops, I don't want this. Get out of here. Okay. So to find the Jacobian, I'll remind you all that we are thinking of this first equation as what f of x1, x2 is equal to. And the second equation is what g of x1, x2 is equal to. And our Jacobian is going to be equal to the 2x2 matrix of partials, f with respect to x1, f with respect to x2, and then g with x1, g with x2. And if it's up to me, yes it is, I'd rather not use the product rule. I don't really want to do the product rule for the derivative of this respect to x1. So I would choose to multiply this out before differentiating. So I'm going to say that my function f, instead of this, I'm going to write it as 9 times 6 is 54x1, and 9 times minus 9x1 squared, and then 9 times -4 is minus 36x1, x2. Similarly, g is going to equal 15x2, and then minus 18x1, x2, and then 3, so minus 3x2 squared. To me, that just seems like it's going to be easier to take the partial derivatives of. Okay, so my Jacobian here is going to equal fx1, which is going to be 54 minus 18x1 minus 36x2. Ugh. Fx2, which is going to be minus 36x1. When you write out these Jacobians and they're kind of gross like this, make sure you give yourself enough space between this thing and that thing so they don't look like you're just subtracting that or adding it to it. And then gx1 is going to be negative 18x2. And then gx2 is going to be 15 minus 18x1 minus 6x2. There's our Jacobian. Taking partial derivatives. Now we're going to plug in each of our points. Let's start off with the easiest one. Let's start with 0, 0. So we plug in 0, 0. We're going to get, let's see here, 54, 0, 0, 15. And you should be able to tell me whether this equilibrium is stable or unstable. I don't really care what kind of thing we think it is, just whether it's stable or not. So is it stable or not? We'll think about what the eigenvalues would be, which should be really, really obvious based on what the matrix is. So you know the eigenvalues are those numbers, meaning if we were going to say we had a thing, we would say we had an unstable node. But when it's nonlinear, you don't really talk about like what kind of thing it is. You just talk about whether it's stable or not. So I would say, great, 0, 0 is unstable. The way I would actually prefer to do this is by talking about the trace and the determinant. So I'll remind you, reminder, we get stability if, and I'm going to say this the right way this time, the determinant is positive and the trace is negative. Right? Because if the determinant is negative, you have a saddle, which is unstable. If the determinant is positive, you can either have nodes or spirals. And we know that on the left side where the trace is negative, that's where you get stable spirals or stable nodes. So to have stability, we have to be in the upper left quadrant of that picture about stability, where the trace is negative and the determinant is positive. So that's why we need those two conditions true. And we definitely have that being true here, right? If you were actually define the trace and the determinant matrix, I don't know what they are exactly. Well, here the trace is 54 plus 15, which is certainly positive, right? Unstable. It's unstable, yeah. So here, my determinant for this one is certainly positive, 54 times 15, but my trace is also positive, 54 plus 15, which means it's unstable because we're not meeting both of those conditions. Okay, let's look at the next one, which was 0, 5. So let's look at the Jacobian, plugging in 0 for x1 and 5 for x2. All right, things might get a little bit messy here. Let's see. So we're going to 54 minus 0 minus 36 times 5. 36 times 5 is 180. And then minus 0 And then negative 18 times 5 is negative 90. And then 15 minus 0 minus 30. Welcome. Again, a relatively easy case here because you can actually just read what the eigenvalues are. So in this case, are my eigenvalues both positive, both negative, or one of each? You can just set those to the side and you can take one shot. Although we're not focusing on that right now. So eigenvalues are negative and negative. So we're thinking we have if we're thinking about what we actually have, we go, oh, it's a stable node, but we're just going to say it's a stable equilibrium, right? We don't care about the nodeness or the spiraliness. So here, 0, 5 is stable. I'll also point out that it meets the criteria for stability. Our determinant would equal whatever this number is, negative 126 times whatever that number is, negative 15, which is certainly positive. I should say negative 126 minus 15 minus 0, but I don't need to write the minus 0 part. And our trace is certainly negative. It's 54 minus 180 plus 15 minus 30, which is a negative plus a negative, which is definitely negative. If you had something like this on an exam where the numbers were a little bit unwieldy, you don't have to calculate the things. I'm not calculating the things. I really should have left this as 54 minus 180 here. And that is 15 minus 30. And you say, okay, cool. I know if I multiply by a negative, I get a positive. And that's all that actually matters. The number, actual value doesn't really matter. All right, 2 more points. I have a feeling the next one's also going to be similarly easy. If I plug in, was it 9? No, 6, sorry. 6, 0 for a Jacobian. Let's see. So let's do the least. So I get 54 minus 18 times 6 minus 0. And then negative 36 times 6. Yeesh. And then negative 18 times 0. And then 15 minus 18 times 6. Even though it's kind of gross, we can see that our determinant is 54 minus 18 times 6, a negative number, times 15 minus 18 times 6, also a negative number. Because 18 times 6 is, I don't know, it's 60 plus 48. That's certainly more negative than 54 is positive. So we have 15 minus 18 times 6 times 15 minus, times 54. Terrible, James. 54 minus 18 times 6 times 15 minus 18 times 6, which is a negative times negative, which is positive. And then our trace is certainly a negative plus a negative, which is negative. So determinant is positive, trace is negative. That means stable. The reason I'm encouraging you to do it this way instead of actually finding the eigenvalues is because although in each of these 3 cases, finding the eigenvalues is really easy, it's not always going to be easy to find the eigenvalues, right? Here you totally could say, yes, the eigenvalues are 54 and 15. Here the eigenvalues are negative 126 and negative 15. And here the eigenvalues are negative number and negative number, whatever they are. It's negative 54 and negative, I don't know, 80, 93, I think. But the point is, we know we can find them relatively easily, but we don't even have to find them. Well, let's look at the last one, though, which might, the last one's good. The last one's going to be terrible. So the last one here, we're plugging in our critical point, this 14/23, comma 31/23. I'm going to look at those numbers again just to make sure that I'm really hoping they're not right, just because they feel really gross. 6 minus x x2 is that. Nope. 6 minus that, minus 20 plus 24. Nope, that's definitely 23. That's definitely 14. All right, that's what we've got. So we're going to plug it in here, and really, really looking forward to this, as you can tell. So 54 minus 18 times 14/23 minus 36 times 31/23. Good Lord. And then over here we have a minus 36 times 31/23. And then down here we have a minus 18 times 14/23. Oh, sorry, times, oops, I got those backwards. Sorry about that. That should have been the 14/23 23rds over there. This should have been the 31 23rds over here. And finally, the last bit, 15 minus 18 times, yeah, 14 23rds minus 6 times 31 23rds. This does seem pretty terrible. Like, really terrible. It's really, really terrible. I don't know. This is where you don't get to use a calculator, right? I mean, no, but like this would be not a test question. So, all right, let's be smart for a second. I mean, okay, for more than a second. You know, let's think about this. 18 times 14 23rds. That's less than 1. So this number is not as big as 18. Yeah, that's not good. Nope, I don't love this either. It's not enough. God, fine. Get out the calculator. Okay, let's see what we've got here. 18 times 14 and 36 times 31. Okay, so we have, I guess, 54 times 23. So we have 1,242 23rds minus, this is the worst problem I've ever seen. Maybe that's not true. I've seen much worse. Don't want to get hyperbolic. Okay, there's the first piece. And that looks like it's going to be a little bit negative, right? 1242 is not as big as negative 52 minus 1116. And then this is going to be, let's see, 36 times 14. We have negative 504 over 23. And then down here, negative 18 times 31. We have 558. And then finally over here, we have, let's see, 18 times 14 again. And then we have 6 times 31, which I should be able to. And then 15 times 23. All right, here's what we've got. We've got 345 over 23 minus 252 over 23 minus 186 over 23. Okay, this is where we're going to try and not do a ton of work. I mean, I know we don't. So I'll point out all these numbers are negative. This number is certainly negative. It's, I don't know, 1242 minus 252 minus 1116. Negative 126 over 23. This is also negative. 345 minus 252 minus 186 is certainly negative. Negative 93 over 23. So let's ask ourselves, is our trace positive or negative? Well, our trace is certainly negative 126 over 23 plus negative 93 over 23, which is for sure negative. Determinant's a little harder. Determinant, yeah, determinant. Good choice of problem, James. It's not the worst thing ever. So let's look at the determinant. So the determinant's going to be that times that, negative 126 over 23. The 23s I'm kind of ignoring. It's negative 93 over 23. Minus that times that. Negative 504 over 23 times negative 558 over 23. Okay, let's ask, excuse me. That's positive. That's positive. And I think it should be obvious which one is the bigger positive number. Is it 126 times 93 or is it 504 times 558? That one, clearly. So you have a smaller thing that's positive minus a bigger thing that's positive that ends up being negative. If our determinant's negative, that means you live in saddle land, although we're not really calling it a saddle. That means we're unstable. So this terrible critical point, 14 over 23, comma 31 over 23, is unstable, like this problem. Cool. So I mean, just like last time, that's kind of the whole gist is, right? You are finding critical or I should say, finding equilibrium points, which I'm really obviously thinking of in my head as critical points because they feel very similar as to how we are finding them. And then we're testing them in the Jacobian to see if we get stability or instability. And if you prefer, although certainly for this one I would not, but if you prefer, you can actually find the eigenvalues. So, and use the same criteria. Although I would caution you against saying you have a spiral or a node. If you're talking about let me write down the words to just try to say something. So for non-linear differential equation systems, where we have something like dx1 dt is equal to some function of x1 and x2, and dx2 dt is equal to some function of x1 and x2. When you find the Jacobian, which is equal to, again, the matrix of partials, fx1, fx2, gx1, gx2. And then when you plug in your equilibrium, so you have like j of x1 hat, x2 hat. I don't really want to write it, but I guess I'll write it out as fx1 of x1 hat, x2 hat, and so on, fx2 of x1 hat, x2 hat, gx1 of x1 hat, x2 hat. All this to say the point I was trying to make a moment ago, which is that once you get to this place, you can find the eigenvalues if you like. But if you find the eigenvalues, so I'll point out, if, for example, your lambda1 and lambda2 are both positive, you wouldn't say we have x1 hat, x2 hat is an unstable node. Don't say that. Just say x1 hat, x2 hat is unstable, or is an unstable equilibrium. Unless your teacher says something else, which I suppose is always the caveat in this class, right? Do it like I say to do it, probably, unless your teacher says to do it a different way. Or whatever she says, I'm trying to show you the easiest way to do it. And if your teacher says to do it a different way, then do it that. But that's the idea, right? If your eigenvalues tell you have an unstable node, say you have an unstable equilibrium. If you have a stable node, stable equilibrium. If you have a stable spiral, stable equilibrium. If you have an unstable spiral, unstable equilibrium. And if you have a saddle, our equilibrium is unstable. If you have a center, I don't know what you say. I think you say it's unstable still. Center being a neutral spiral, right? Where the real part is zero. But basically, you're not commenting on the actual shape of things. You're just commenting on the stability or instability when you're talking about non-linear differential equations. Cool. So we could do another one, but I feel like these kind of just feel like the same every time. To a degree, right? The finding the equilibrium is sometimes challenging. But after that, the Jacobian is pretty much always the same kind of thing. Where you're just finding your partials, setting them equal to zero. Sorry, finding your partials and plugging in your equilibrium. Is there anything else I want to say about that? Not really. Yeah, so everyone grab a practice exam. So there's one double integral question there at the beginning, and the rest of it's all about systems of differential equations. I plan to write solutions for this and post them after class on Friday, but I also plan on going over it in class on Friday. So that's kind of the, I do think you all should attempt to do this before class on Friday. Question, Christian.
I was just gonna say like what's one thing you want us to like know like really well going into this test? Because like a lot of it is just like a lot of it's just like major simple stuff, but like in general, what
I mean, you definitely should know how to, at the drop of a hat, find the eigenvalues and eigenvectors. And looking, so I will point out, looking at his previous exam, I mean, so I'll just, if you can hand me one of them actually. So I'll point out But on this exam, I think I threw in a couple extra, like writing the systems as equations. But most of these questions came from his practice from before. Specifically, I'll point out that there definitely was a couple questions where you had to solve the following systems of differential equations. And I will point out, there was one on the exam that was complex. He didn't give initial conditions on his. I did to make it harder, to give you the practice, because maybe he will. So I would say work on those. I'm trying to think of what else. And what else is, I don't know, what did all you guys talk about in class today was nonlinear stuff again? Did he, like the spiral or the neutral spiral? Right, right, yeah. So what he's probably talking about there is the fact that if you have, I don't get that order here. So that if you have a system like, try and make it, sorry, one sec. Now I have to think about the system like dx1 dt equal to dx2 dt equal to, I want my trace to be 0. So I want this to be something like 3x1. And then if my trace is 0, I'm going to determine it to be positive. Sorry, it always takes a minute to make these come out right. So let's see, let's go negative 3x2 over here. That's a negative 9. I want to be plus something. Sure, a minus 4x2, a 5x1 here. That should work. If we had a system of equations like this, and we want to find the solution and also talk about what it looked like. I should say, I always say when I say what it looked like, what I should really say is we want to talk about what the equilibrium looks like, whether it's a spiral, a node, stable, unstable, whatever. So if we do this one here, well, again, our matrix is just going to be 3, -4, 5, -3. And we're going to find our eigenvalues. So eigenvalues, good times. It's going to be the determinant of 3 minus lambda, -4, 5, -3 minus lambda. You should start here when you're finding, like if you're going to find the determinant this way, doing determinant a minus lambda I, you don't need to write down like a minus lambda I. You should just subtract lambda from each of your diagonal spots. Determinant, that's going to be 3 minus lambda times -3 minus lambda minus -4 times 5. These numbers are not going to come out as nice as I wanted them to, such is life. And then simplifying this, we get lambda squared. You always get lambda squared. Like always. It is unavoidable. You always have something minus lambda times something minus lambda. You get negative lambda times negative lambda, which is always lambda squared. And then we have a plus 3 lambda minus 3 lambda, so we have a 0 lambda there. And then we have a -9 plus 20. So we have lambda squared plus 11 equal to 0. Lambda squared equals -11. Lambda equals plus or minus the square root of -11, which we typically write as plus or minus I root positive 11. So there's our eigenvalues. And at this point, we could classify. I think we should still solve it because it's good practice and we got 10 minutes to fill. But at this point, you can say, great, my eigenvalues are lambda equal to 0 plus or minus I root 11. The real part is 0. That means we don't have a stable spiral or an unstable spiral. We have what's called a neutral spiral, where you just keep circling around and around and around. You don't oscillate outwards, you don't oscillate inwards. So that means we have a neutral spiral around our equilibrium, 0, 0. That's how we know that your eigenvalues are purely imaginary. All right, let's go ahead and do the rest. So we're going to solve this system. So we need to find the eigenvectors. So take one of your eigenvalues, either the one with the positive or the negative part. It doesn't really matter, although I think the standard choice is always to pick the positive part. So we're going to say that lambda is equal to I root 11. And then we're going to find the corresponding eigenvector. And I'm going to do it the way that he seems to prefer to do it, which is actually the way we find the other ones, is just by trying to solve a times your vector equal to lambda times your vector. So in this case, it's going to be 3, -4, 5, -3 times our vector, which he likes to call v1, v2, equal to our eigenvalue, so I root 11 times our eigenvector, v1, v2. We almost always use the first equation. So we're going to say that 3 times v1 minus 4 times v2 equals I root 11 times v1. Collect all the like things on the same side. So bring all the v1s to one side, all the v2s to the other. And normally I'd bring all my v1s to the right, but here I guess I still could. It doesn't really matter. So -4 v2 equals -3 v1 plus I root 11 all times v1. He would probably divide everything by -4. I would not. I would pick my eigenvector right now. So I would probably choose either my eigenvector to be v1 equal to -4, v2 equal to -3 plus I root 11. Or if I was feeling like I might change the signs to be +4 and +3 minus I root 11. Either choice is valid, but you have to pick one. Or something else completely. Meaning he would have probably picked, annoyingly, sorry, brain, v2, not v2, sorry. He would have divided both sides by -4. Said v2 is equal to -3 plus I root 11 divided by -4 v1, and picked v1 equal to 1 and v2 equal to -3 plus I root 11 divided by -4, which seems like the worst choice you could make. But they're all valid choices. Each of these 1, 2, 3 choices here are multiples of each other. So they're all technically eigenvectors for the same eigenvalue. Well, so I'm just looking at this equation. 3 times v1 plus -4 times v2 equals I root 11 times v1. You're asking about this choice right here. So when I find an eigenvector, I find the easiest way to, watch this right now, the easiest way to solve this equation. That's what we're doing. We're finding a solution to that equation. I should be more specific. There is an easier solution that we're not going to pick. 0, 0. It's never a choice, right? You don't want to pick that equal to 0, that equal, even though it would be a solution, because -4 times 0 is equal to whatever that is times 0. But I want to find just some solution. The easiest way to find a solution is to say, great, pick v1 equal to the coefficient there and v2 equal to the coefficient there. Because it's sure, right? If I plug in v1 equal to -4 and v2 equal to -3 plus I root 11, then both sides of this equation are -4 times -3 plus I root 11. And they have to be equal to each other. So that's how we're making that easy choice. And you can always, it's always valid. So that's what I would prefer to do. He's kind of doing that over here too. He's saying, cool, pick v1 equal to the coefficient of v2, which is 1, and pick v2 equal to the coefficient of v1. Or if you prefer, you can say I'm substituting in -4 for v1, and then -4 times this has to equal -4 times v2, so v2 has to be the -3 plus I root 11. I just multiplied top and bottom by -1 because I would prefer to have more things being positive versus more things being negative. But whenever you're trying to solve this, like if you have 3 times v1 equal to -7 times v2, if that was your equation for your eigenvector, we can totally find our eigenvector is going to be, well, cool. V1 is the multiple of V2, and V2 is the multiple of V1. It always works. All right, and then we do, so I think I've come around to doing it his way, even though, yeah, whatever. So then we would say our solution here, oh, I skipped a step, sorry, one step. We would then break up our eigenvector as the real part, 4, 3, plus the imaginary part, which is negative I times 0 root 11. And then we would write our solution as, that's our, yeah, as x equal to, he doesn't like to write the c in the beginning. He just likes to write e to the lambda t times v, which is totally fine. So it's e to the lambda, this lambda, I root 11 t times our vector v, which I should have written, but I'm a fool. So well. So here's what's interesting about this one. There isn't a real part. So we don't get bigger and bigger and bigger or smaller and smaller and smaller because you don't have the e to the number times t. You just have the e to the imaginary thing times t. And this is going to become, well, that's going to become cosine of root 11 times t plus I times sine of root 11 times t. And there isn't any e to the 2 times t to be out in front getting larger or smaller. That's why this is a neutral spiral that just keeps going around and around and around in the same circle, because you don't get bigger and bigger values of x and y or smaller and smaller values of x and y. And then you still have the vector v here, which I guess I'll, sure. So then, sure, we might as well finish this off in the last 3 minutes we have here. So then writing our solution, here's what we've got. We've got cosine of root 11t plus I sine of root 11t multiplied by the vectors 4, 3 plus negative I times 0 root 11. I suppose I shouldn't have the negative I in front, actually. That's kind of a mistake. It should always be I times whatever, not negative I. I just kind of brought it because I wasn't thinking. That should be a plus I times 0 negative root 11. Sorry about that. And then we FOIL it out, but the foiling always kind of works exactly the same way every time. So we FOIL this out, we have that x is equal to cosine times 4, 3, and then check this out. The I times I is I squared, which is negative 1. So you have negative sign times that vector there. So you end up getting cosine of root 11 times t times the vector 4, 3 minus sine of root 11t times the vector 0 negative root 11. That's one piece plus I times sine of root 11t times 4, 3 plus cosine of root 11t times I times 0 negative root 11. The I factors out and you have cosine of root 11t times 0 negative root 11. This solution probably looks like it's missing something to you. Because it kind of is. It's missing the e to the something times t part that's usually there. But we don't get that here because our eigenvalue was purely imaginary. We don't, right? So, right, usually your eigenvalue is a plus or minus bi, and you usually get an e to the at times a cosine of bt plus I sine of bt. We're missing this part because our a was 0, and e to the 0 is just 1. And then if I was doing this on the exam, I think he just likes to then say like that this is your g of t, and this is your h of t, and your general solution x of t is equal to c1 g of t as a vector plus C2H of T. That's what he usually writes when he's writing these solutions, right? He doesn't like write it all out. So yeah. That's your general solution.
So we would want to simplify.
Well, I think he considers it simplified all the way. I don't. So on the other hand, I know we're out of time, and if you need to go, you need to go. But if it were me, I would probably choose to do the following, just because this is how I like to do it. I would say I'd actually combine the parts. So I'd say, cool. I like to write this part here as 4 cosine of root 11t minus 0 for the first part, and then 3 cosine of root 11t plus root 11 times sine of root 11t plus, we're almost done, sorry. And then you have the other part here. I forgot that there's a class in here on Monday. 4 sine of root 11t. And then the second part is 3 sine of thing minus root 11 cosine of root 11t. And then you put a C1 and a C2 in front of this. That's how I'd write it. And then if you had to find the C1 and C2 because you're given initial conditions, you plug in T equal to 0. Remember that cosine of 0 is 1, sine of 0 is 0. Solve for C1 and C2. All right, we should stop because it's awesome. All right. Make sure everybody got a practice exam. Definitely try the practice exam, and we'll talk about it on Friday. Because today